Analytical Chemistry 1, Lesson 13. Let's look at some examples of using the t-test in various situations. In Southeast Asia, the geology is such that there are places with rather high concentrations of arsenic in the ground. When a new well is dug, the water has to be tested for its arsenic concentration. If the concentration is too high, the well cap is painted red to alert the villagers that the water from that well can be used for washing but not for drinking. When painted green, it's acceptable for drinking. Many years ago, the World Health Organization had set an arsenic concentration level in drinking water at 50 parts per billion as the acceptable concentration. But studies over the years found an increased incidence of cancers caused by the arsenic, so the standard is now set at 10 ppb. In your work with an NGO working in rural Bangladesh, you carry out tests to identify wells with arsenic and you mark them. Changes in rainfall patterns can lead to changes in groundwater flow patterns, so the wells need to be monitored over the years to ensure their safety. When you arrive at a well, you take 6 water samples throughout the day. Your tests gave an average of 8.3 plus or minus 2.9 ppb. If you are required to provide a 95% confidence conclusion, do you paint the well green or red? Well, the first question, is this a one-tailed or two-tailed statistical test? Well, our concern is whether or not the arsenic concentration is greater than 10 parts per billion. Sounds like a one-tailed test. What is the null hypothesis? Well, it is that everything's okay, the concentration's acceptable. Any variation we see as a result of statistics and not because of something physically or chemically being wrong. So the null hypothesis is arsenic is less than or equal to 10 parts per billion, and from that we identify the alternate hypothesis as arsenic being greater than 10 parts per billion. We perform the t-test by calculating the t-statistic with an equation that is just a reorganization of the expression we have used for the confidence limit. We use this equation. This is our calculated t-statistic, minus 1.436. We must compare this to a value from our t-table. First of all, we need to know the number of degrees of freedom in our data set. Since we acquired 6 samples, nu is equal to 5. Here's the t-table. First of all, note that the table is for a two-tailed t-distribution. Find the correct number of degrees of freedom. So which column do we use? Well, we're after 95% probability, one-sided. That means that there is 5% excluded at the high end of the distribution. The 95% column in this table refers to the two-tailed situation, which would have 2.5% at the high end and low end. By comparison, the 90% column has 5% at the high and the low end. Therefore, the 90% column for a one-tailed test provides the right t-value. Our tabulated t-value is 2.015. Our calculated t-statistic is smaller than that from the table, so we conclude that our data is not able to reject the null hypothesis. Therefore, we declare the water from the well to be acceptable, we paint it green, move on to the next village. Now here's your data again. We see that the calculated t-value is less than, in fact it's negative, the tabulated value. And since we have the right side one-tailed test, we are not able to reject the null hypothesis and we paint the well green. But what if your tests produced a sample average of 11.7 parts per billion instead? Would this change things? Well, now the average is greater than the acceptable concentration level. 11.7 is as far above 10 as 8.3 is below 10. Now the calculated t-value is positive 1.436. The tabulated value is still 2.015, which is still greater than 1.436. We are still not able to reject the null hypothesis. We still paint the well green. What this test means is that with 6 tests, which produce an average of 11.7 with a standard deviation of 2.9, we cannot conclude that such results are anything other than just normal statistical variations around some mean that could be less than 10 parts per billion. What if the average was 12.5 parts per billion? Well, now the calculated t-value is 2.112. The tabulated value is still 2.105, which is now less than 2.112. Now we reject the null hypothesis and paint the well red. One last variation. What if you still had 11.7 ppb sample average, but used a more precise technique so that the standard deviation was 1.9 ppm instead of 2.9. So only the standard deviation has changed. We plug it in and find that the calculated t-value is 2.192. We're still comparing this to 2.015, so we reject the null hypothesis and paint the well red. Here is another problem you might encounter. You're employed at a pharmaceutical company. One of their products is a tablet that is designed to deliver 300 milligrams of a drug called gabapentin, used to treat neuropathic pain, among other indications. Your task is to ensure that the production process is stable and producing pills with the correct amount of the active ingredient. Now, around 38% of each tablet consists of non-medicinal ingredients that help form the tablet, extend the tablet's shelf life, and help its absorption in the body when swallowed. You take 9 tablets, dissolve each in water to form a solution that you analyze for the active ingredient. Your measurements produce a result of 312.4 plus or minus 9.2 milligrams per tablet. At the 98% probability level, is the manufacturing process still working well? You have to consider the possibility of having too much as well as too little active ingredient in the tablet, so this is a two-tailed problem. There are 9 minus 1 equals 8 degrees of freedom in the data set. The null hypothesis is that there is 300 milligrams of gabapentin in each tablet. The alternate hypothesis is that there is not 300 milligrams in a tablet. To find the expected tabulated value, look here at the t-table. For 8 degrees of freedom and 98% confidence, we find the tabulated t-value to be 2.896. The calculated t-value is 4.043, which is much larger than the tabulated value. Therefore, we cannot reject the null hypothesis and conclude that there must be something, we can reject the null hypothesis and conclude that there is something wrong with the manufacturing process. There is just not the right amount of gabapentin in the tablets. Now here's another study. You're employed as a field scientist with an environmental company. Your company has been hired to monitor the pH of the water in a small river that is downstream from a manufacturing plant. They carefully treat the water they use in their production process and then send the treated water back into the river. They, however, need to monitor the river's pH, which might help to identify problems with their process. They need to know if the river's pH is changing significantly. Your task is to take several water samples over the course of a day to determine the average pH of the water. Do this every month to see if there are statistically significant changes. The first month, you took 8 samples. You determined the river's pH at 6.83 plus or minus 0.05. In the second month, you took 9 samples and determined the river's pH is 6.94 plus or minus 0.04. Is this a problem? Do you alert the company to suggest they look for a problem? In this situation, we are comparing 2 sets of data and asking the question, are they statistically the same or are they different? This is a two-tailed t-test. We can imagine that the river pH could increase, become more alkaline, or it could decrease, become more acidic. We have to allow for both conditions. We also need to choose our level of confidence, so let's look for the differences at the 95% level. The null hypothesis is that there is no difference. The alternate hypothesis is that statistically there is a difference in the average pH. Now the arithmetic is a little more complicated, but the equations are derived similarly as before. You can find a set of equations for the situation where the 2 sets of data have the same standard deviation and a separate set where they do not. The first set of equations reduces to the second set under the right circumstances. So we will just focus on the more complex but widely applicable set of equations. First, you need to pull together the variance, the standard deviation of the 2 data sets. For our situation, we have 2 standard deviations, and n equals 8 for the first and n equals 9 for the second. Plug in the numbers to find that in this case, the pooled standard deviation is 0.0449. Note that it is essentially the average of the 2 standard deviations. That there is one additional sample for the second case is why it skews slightly towards the 0.04 value. We can now calculate a t-value comparing these 2 data sets. The equation is given here. We plug in the numbers and come up with 5.037. We now need to compare this value with the right number from the t-table. we have indicated that we are asking a two-tailed problem at the 95% level, so we can use the 95% column directly, but first we need the number of degrees of freedom. Now this is another complex equation to combine the two data sets. We have a total of 17 data points and 2 averages. However, the weighting factors are different. The equation is, again, rather complex, but look at it carefully and you will see the symmetry. Note how the units arising from the standard deviation terms all nicely cancel out, since degrees of freedom is a unitless number. Also, the arithmetic produces a non-integer, so we round it to the nearest integer and obtain 13 degrees of freedom for this combined data set. Pull up our usual t-table, and we have a problem. U equals 13 is not listed. Well, we could go to the internet and find a more complete table, which is pretty easily done. Or we could go to Excel and use the t.inv.2t function for 0.05 probability and 13 degrees of freedom. We would find its value is 2.160. Or we could just look at this table. We see that for 10, the value would be 2.228, while for 15s, it's 2.131. We know the value for 13 is somewhere between these two, but whatever its exact value is, and we now know it would be 2.160 if we had gone to Excel, in any case, it's still considerably less than the calculated t-value. Statistically, we can reject the null hypothesis and go to the company and suggest that something is amiss. They will start studying their procedures and operations, and you will start performing more frequent tests both downstream and upstream to see if it is indeed the manufacturing facility or if it might be some natural process due to the changing weather, but something is changing the pH of the river. There is one additional t-test that you will need to know how to perform, the paired t-test. Go back to this manufacturing facility by the river. It is a very expensive and serious problem if, for instance, their effluent is raising the river's pH. Your findings are very important, and we need to be very certain of our conclusions. Our findings are not that the plant is polluting the river. Our findings are only that, statistically, the river's pH is changing. Since the claim is so serious, we want to make sure that there is nothing in our procedures that is awry. So our company sends another field scientist, and together, each of you take 10 water samples over the course of 3 days. You analyze them individually. Your sample number 1 is paired with your colleague's sample number 1, and so forth for 10 samples. The question you are asking now is, are our 2 sampling procedures equivalent? Or was your original data possibly flawed due to some unknown systematic error? So here are your paired data. We find the difference between the 2 sets of data for each pair of measurements. Find the average and the standard deviation of the differences. Ignore the negative sign in the average. It just depends on who you call analyst 1. Find the standard error of the mean, which is just the standard deviation divided by the square root of the number of pairs of samples, which is 10. The null hypothesis is that the 2 data sets are statistically equivalent and that your work is not affected by any additional sources of error. The alternate hypothesis is that there is an additional problem that is causing the 2 experiments to produce statistically inequivalent results. We calculate a t-value for this data set, which is just the average of the differences divided by the standard error. Its value turns out to be 1.960. Compare this with the tabulated value. There are 10 minus 1 degrees of freedom, 10 minus equal to 9, and we seek confidence at the 95% level. We look it up in the table and we find it is 2.262. We have t-calc less than t-table, so we cannot reject the null hypothesis. This supports your claim that your work to date is statistically sound. We've seen 4 different kinds of t-tests, and you should be able to work through these when you have the equations at hand. The 4 tests are a one-tailed test against a known value. We were deciding whether or not the arsenic concentration in the well water was too high or not. A two-tailed test against a known value. Were the gabapentin pills still delivering the stated dosage? A comparison of 2 data sets. Had the river's pH changed since we last tested it? And a comparison of 2 paired data sets. Are the 2 analysts getting the same results? These are some of the important tests you can do with your data when needing to draw conclusions from them.